presentation is by Anwer Al-Kaimakchi, and the title is Experimental Study on Flexural Behavior of Concrete Girders, Prestressed with Stainless Steel Strands.
Good afternoon. My name is Anwer Al-Kaimakchi. I'm a PhD candidate at the FMU FSU College of Engineering. Rambo-Roddenberry is my PhD advisor. My presentation today is experimental study on the flexural behavior of concrete girders pre-stressed with stainless steel strands. This presentation is part of a big project funded by the Florida Department of Transportation. The main goal of this project is to study the use of stainless steel strands in the flexural members in the bridges. So you can see the background picture of my presentation. I have 5 spools. 3 of them are carbon steel strands, and 2 of them are stainless steel strands. Stainless steel strands are relatively new to the construction industry compared to the black steel strands that have been around in the US for around like maybe 10 years. We can see they don't hold rust on their surface, so the main objective of using them is to prevent corrosion and structural members in aggressive environment. So to start, this is the outline of my presentation. I will start with introduction and objectives, talk about the mechanical properties of the strands, then talk about the girders, fabrication, flexural tests, analytical model, and preliminary design guidelines. And then I will finish with conclusion. So corrosion is the most common type of deterioration in coastal bridges. It could happen in piles where water level fluctuates, or sometimes in girders. And in some cases, there were corrosion in the slabs. So there is a need for reinforcement that is corrosion resistant. One of them is the Duplex high strength stainless steel strands, grade 2205. It is a 7-wire low relaxation strands. It is a corrosion-resistant strands, has the highest strength and corrosion resistance among other stainless steel grades. So this is, they call it HSSS. There are other grades. This is the best option among those other grades. It has guaranteed ultimate tensile stress of 240 KSI, and it has a guaranteed ultimate tensile strain of 1.4%. The issue here, it doesn't have as much ductility as the carbon steel strand, so special attention needs to be taken when this material is used in design. And then currently, they are available in 2 sizes, 0.5 inch and 0.6 inch in the US. So as with a new material, it cannot be implemented in real project before research and testing. So we started with material testing. We tested those strands in tension and bonding. And then the main objective is to investigate the flexural behavior of this material and compare the result with a control girder, which is pre-stressed with conventional steel strands. Then implementation, you need to define a minimum guaranteed ultimate stress and strain. So you need to propose an ASTM for both designers and manufacturers. So if a manufacturer wants to produce this material, they need a guideline. And then for a designer, you need to know your mechanical properties of the strands. And then you need to come up with the design guidelines for bridge designers to use, such as like ACI or Eurocode or AASHTO. And then for the long term of using this material, it will increase the service life of the bridge and then reduce the maintenance and then inspection costs. Starting with the mechanical properties, we can see the mechanical property, the stress strain curve of the stainless steel strands, the red one, is fundamentally different than that for the carbon steel strand. It has a lower elastic modulus, and then it has a lower ultimate stress and strain. And then we can see that it has a rounded stress strain curve up to failure. So there is no plateau, there is no yield, like defined yield, similar to the carbon steel strands. So the design guidelines developed for concrete members pre-stressed with carbon steel strands cannot be used for the stainless steel strands, and different design guidelines needs to be developed. The most significant difference is the low ductility here. The minimum guaranteed is 1.4%. For the carbon steel is 3.5%. Usually it's way higher than 3.45%, like around maybe 5%. So ASTM A4116 has been around for so long. It's mainly for steel strands. It cannot be used for stainless steel strand as you saw before. Stainless steel strand has different mechanical properties. So recently this year, April 2020, a new ASTM has been published, ASTM A1114. This defines the minimum requirement for the stainless steel strands. We can see here that for the stainless steel strands, they have a slightly higher area, but lower strength at 1% extension, lower breaking strength. The ultimate stress is lower, 240 compared to the 270 KSI, and the ultimate strain here is 0.014. And then for the carbon steel is 0.035. The stainless steel strands that we used in this project had like satisfied all the requirements specified by the ASTM A1114. And then if you can see the ductility, it had a higher ductility than the required value. Girder fabrication, we chose AASHTO type 2, 40 feet long. We had 4 girders. The initial stress for the conventional strand was 75%. We had to go lower than this value because of the ductility issue in those strands. So we tensioned the stainless steel strands to 62.2% of the ultimate. The specified strength for the girder was 10 KSI. For the deck slab was 6.5. The design method was force equilibrium and strain compatibility because there is no design guidelines specified for the stainless steel strands. And those girders were fabricated at Durstress casting yard in Leesburg, Florida. You can see here like some pictures during fabrication. As I said before, we had 4 girders. The first girder is the control girder. It had conventional strands, 11 strands, and then it had conventional steel rebars for transverse reinforcement, the stirrups. Girder 2 had stainless steel strands. We matched the number of the strands with the control girder, and girder 3 had the same initial pre-stressing force as the control girder, so we had to increase the number of the strands to 13. Girder 3 and girder 4 are identical, except that girder 4 had stainless steel rebars. Girder 3 had GFRP rebars. GFRP is glass fiber reinforced polymer. They are corrosion-free rebars. Stainless steel rebars are corrosion-resistant rebars. And then for girder 2, the shear reinforcement was GFRP as well. We wanted to have a girder that is corrosion resistant as much as possible. And then for the control girder, we had conventional steel rebars. It's important to mention here that the shear design for our girder was based on AASHTO bridge design specifications, and then it was designed for the conventional steel rebars. And then we replaced those straps on the basis of 1-to-1. So we designed it based on carbon steel, and then we changed it with GFRP or stainless steel rebars. Here is a picture of the shear reinforcement. This is girder 1. We can see those carbon steel rebars. There is kind of frost. For girders 2 and 3, we use GFRP. They are corrosion free, and then for girder 4, we used stainless steel rebars. For the flexural test, we tested our girders in 4-point loading scheme. The test was done at the Florida Department of Transportation Structures Research Lab in Tallahassee, Florida. And then the first girder 2 was tested. Girder 2 was the first one which was tested, and then we can see here, this is the shear reinforcement. This is the layout of the reinforcement for girder 2. We can see here, those are the GFRP stirrups. So we loaded the girder, and then slightly after cracking, we saw a shear crack at the end region, and we decided to unload the girder because the main objective of this research was to study the flexural behavior, the flexural behavior of the member, and then we didn't want the member to fail in shear. So after we reviewed the literature, we decided to externally reinforce our girder with external clamps. Those clamps did not influence the rotation or the behavior of the girder. We can see here girder 2, girder 2 before adding the clamps. Here adding the clamps, and then this is the girder 2 after we add the external clamps. Those are the shear cracks that initiated and the first loading. I hope I can show you a video of girder 3. Yes, it's working. So this is, you can see here, this is the load here, and then this is the deflection at midspan, and then those are the strain readings in the midspan region. Those are 3 strain gauges. You can see this is a GoPro camera from here. You see the girder exhibited many flexural cracks before failure, and the deflection was large. We had deflection of almost like 6 inches here, and then it failed. We saw here it failed due to rupture of all stainless steel strands because of their low ductility. It failed while the concrete in the compression zone was still intact, but then it gave us a good warning where like many flexural cracks formed. So starting here, let's compare the load deflection between girder 3 and girder 4. Girder 3 and girder 4 had the same pre-stressing force. Both of them were reinforced with stainless steel strands, except that they had different stirrups. Girder 3 had GFRP, girder 4 had stainless steel stirrups, and then we saw a reduced in their flexural behavior. And then after examining the girders after the test, we saw that many cracks originated in girder 3, and then we didn't see those cracks in girder 4. So the effect of using GFRP was that our load carrying capacity was reduced. Girder 4 had around like 12.4% higher load carrying capacity. Comparing girder 2, if we investigate the load deflection between girder 2 and girder 3, they had the same stirrups. Both of them had GFRP, but they have different pre-stressing force. So here we have, for girder 3 we have 13, the blue one. For girder 2 we have 11 strands. We saw we saw that the flexural behavior was reduced. And then the main reason for that was because the interface region between the girder and the deck slab was smooth, so we didn't roughen it during fabrication. And also GFRP rebars do not provide high strength in their transverse direction compared to their vertical direction. And also because of the low elastic models of the GFRP rebars compared to the carbon steel or stainless steel rebars. Girder 3 had 18.2 increase in the initial pre-stressing force because of the 2 additional strands, and then this did not influence the deflection, but then it did influence the ultimate capacity. As we can see here, it increased by 17.5%. Investigating the girder 1, which is the control girder, with girder 4, they had same initial pre-stressing force. We can see here that the flexural behavior of the control girder and the one with the stainless steel strands is different. The control girder was not loaded up to failure. It was unloaded before failure. It was saved for future shear test. But then the stainless steel girder was loaded to failure. And then we can see here that the ultimate load carrying capacity of the control girder was 23.7 higher than that. The load carrying capacity of the girder with stainless steel strands was 23.7% higher than of the control girder. Girder 4 also ruptured failed due to rupture of the stainless steel strands. We can see here that all of them broke at failure, while the concrete in the compression zone was still intact. We developed an analytical model to validate the experimental results. The model was developed based on force equivalent strength compatibility. And then we can see that our analytical results were in good agreement with the experimental results. This is for Girder 1, the control girder, and then this is for Girder 4. Preliminary design guidelines for the flexural design concentration for conventional steel strands based on AASHTO girders are designed to have the strands yielded before the concrete in the compression zone crushes. This cannot be implemented for stainless steel strands just because of the differences in the mechanical properties. So we have three design concentrations when we use stainless steel strands. The first one is to choose your member to fail due to crushing of concrete, and then here you have to have your strain in the top fiber, strain in your top extreme compression fiber reach 0.003 before the strain in the bottom layer of strands reaches the ultimate value of 0.014, or you can have the balance condition where both the strain in the extreme compression fiber and then the bottom layer of strands reach their ultimate values simultaneously, and then both of them fail at the same time. It's theoretically possible, but experimentally it's kind of very hard because of the variance in the material properties. And then the third option is to have your member to fail due to rupture of the strands, where you will have the strain in the bottom layer of strands reaching 0.014 before the strain in the extreme compression fiber reaches the ultimate value of 0.003. So if we choose to have our member to fail due to crushing of concrete, we can see the flexural behavior of the member is a function of the strain and the bottom layer of the stainless steel strands. Here we can see the higher the strain in the bottom layer of strands, the higher curvature, which means the higher ductility and deflection. And then also we can have the tension force high if we have a higher strain. For the balance condition, this is the optimum solution because we can achieve the highest curvature, which means the highest deflection. If we choose our member to fail due to rupture of the strand, then the flexural behavior of the member is a function of the strain in the extreme compression fiber. The higher, the better, because if we have this value high, then our curvature is high, the deflection is high, and also the compression force from the concrete is high. So in conclusion, stainless steel are now a viable option for concrete structures in extremely aggressive environment. The stress strain curve of the stainless steel strand is fundamentally different compared to that of carbon steel strands. During fabrication of the stainless steel girders, we did not require any additional equipment or procedure different than those used for carbon steel strands, so the crew did not experience any differences while fabricating those girders. From the experimental results, we observed that the post-cracking behavior of the stainless steel girder was different than that for the carbon steel girders, mainly because of the differences in the mechanical properties. The capacity of the stainless steel girders increased up to failure. We don't have a plateau as we usually do for the carbon steel girders. The stainless steel girders exhibited many flexural cracks before failure, which is a good indication that the member is reaching its ultimate capacity, which gives us a sign that we need to evacuate or do something. And then rupture of the stainless steel strands might be considered a brittle failure. It is a brittle failure, but in our test, the girders exhibited a large deflection around 5 to 6 inches. Thank you so much for giving me the opportunity to present, and then I welcome any question.
Thank you. This was to be understood, I think. Do we have any questions?
Yes, Bruno Girder, yes. You have first a comment and then questions. The first comment is that it would be better to use international units because you are using American units, but it's not international units. So I had some.
Sorry about that.
So I had some difficulties to transfer into megapascal, for example.
Yeah, sorry, I realized this today when I saw the presentations before me. Yeah, sorry about that.
Yes. So if I look at the ultimate limit states of stainless steel, you have about 250 KSI, which is about 1,700 megapascal.
240.
But with the carbon steel, we can use now 2,000 megapascal, or maybe 2,100 megapascal.
Yes.
So it means that we can have a higher strength with the carbon steel than with stainless steel.
Correct.
Yeah, that's just a consideration. And then in your paper, you say that stainless steel girders can achieve ultimate capacity and deflections as high as girders prestressed with carbon steel strands. I think it's right for capacity, ultimate capacity. But for deflection, it's more difficult to say that because first, your girder number 1 was stopped before failure, complete failure. So it means that there was still a capacity of deformation, probably. And then when we look at the law, the behavior law of carbon steel, we have a greater ductility than with stainless steel. So it means that in the girder, we can have more ductility with carbon steel than stainless steel.
That's the main issue in design. Yes, correct.
The main issue, huh?
Yeah, the main issue in design. Sometimes the design is not controlled by the strength. So if it's controlled by service, you will add more strands. And then in this case, you will have many stainless steel strands where you can achieve as close deflection to those pre-stretched with carbon steel strand. I see your point. Yes, it's an issue and we're working on that. I'm not presenting all the results here because after this, after I submitted the paper, we built 5 more beams and then we validated our analytical model and then we did a parametric study and then we designed the bridge. So it's more than this presentation.
Okay, thank you.
Thank you so much for your feedback.
Any other questions?
I do. I was wondering about the kind of serviceability because sometimes design of pre-stressed beams is governed by serviceability criteria like crack widths, which are very important if you're using conventional steel because of the protection against corrosion. So if corrosion of stainless steel strands is not so much of a concern, would you end up being able to use a smaller quantity of steel, or how would that affect things? Have you looked at that?
A small what?
Would you be able to use a smaller area of stainless steel because you're not being governed by SLS? And would that, have you thought about that and how that might change designs?
That's a very good point. I think based on our results now, the crack width is not an issue just because the stainless steel strands was tested for corrosion under corrosion-like effect, and then it performed really well. It wasn't done by us; it was done by other group. So I think the crack width is not an issue. I think they will permit even, I don't want to say wider crack, but then the limit now would be good for the stainless steel strands. So that won't be an issue in design. Especially if those strands will not be used for long girders because of their cost issue. I think they will be used in, I would say, short to mid-span bridges in coastal areas where like corrosion is extremely aggressive, like in Florida. So they will be used selectively in special cases. they won't use them all the time.
Sure. Okay.
Any other questions? I have two questions to you. One, as you mentioned now, when answering, you mentioned the cost issue. So how are the costs for your prestressing stainless strands? That's one question. And the other question is, did you used glass fiber stirrups? Did you consider using also glass fiber or basalt strands for the prestressing?
The first one is, how much is the difference, or the cost one? I didn't hear it well, sorry.
Well, I'm sorry. The stainless steel is obviously more expensive. And how much more expensive is it?
Currently, it's around 10 times more expensive than the carbon steel. But then with that being said, there is only one manufacturer producing this strands. So we expect the cost to reduce if the material is being used more, because the production, and then more producers will start to produce this material. Currently, stainless steel strands have been deployed in 10 bridges, mainly in piles. I'm talking in the United States. So we expect the cost to reduce, but currently it's 10 times. And then the second question, the project is focused only on stainless steel strands. Florida Department of Transportation is trying to find an alternative to carbon fiber and basalt fiber. So they want to have an alternative, and then the designer will get to choose carbon fiber or basalt fiber or stainless steel as the main longitudinal strands. We did not think about using them for the stirrups. The GFRP was an option, and then we chose it, but then it didn't help us well. So we're not, like the main focus is the flexural behavior of the strands, not the shear.
Okay.
Yeah, there is a nationwide interest in this material, and then there is a federal, like a project funded by the Federal Highway, was initiated 6 months ago, and then this will explore the use of the material more widely.
Okay, thank you.
There is a comment of Steve Nolan.
Oh yeah, okay.
Yeah.
Yeah, I can see it now. For the AASHTO, SLS is usually controlled by two limits for tension depending on the environment. For HSSS, it is envisioned that the higher tension stress would be permitted, but still less than the modulus of rupture. This is the same as for the CFRP strands.
Mm-hmm.
Yes, Steve.
Okay. Okay, that was the information, I think.
Yes, I know,
Yeah.
Steve. I know Steve Nolan. Thank you.
Yeah, and then we conclude our session. And I would like to thank you all, presenters and participants, and also my co-chairman. And thank you very much.